Hello students, welcome back. In the previous class, we have derived an equation for concave spherical surface. Okay, I'll just write the equation over here because we need in this particular topic. That is N2 by V minus N1 by U is equals to N2 minus N1 divided by R. This is what we have derived in the last class. Now, there are certain topics which are very basic and you can study them by yourselves, such as there is a topic lenses. There are different types of lenses are described. You can go through that by yourself, which is not that too important also. Okay, just the name of the lenses are there. Important topic is converging and diverging action of lenses. That you can go through by yourselves. Other topics such as optical center, which you already know, which is the basic of a lens. The center of a lens is known as optical center. Let's go through that. Another one is focus and focal length. Okay, focal length is a distance between principal focus and optical center that you already have studied till now. Now, this derivation which I am going to do today is one of the most important in this chapter. Okay, that is lens maker formula. Now, from the name itself, you can make out that the lens maker formula relates the focal length of the lens to the refractive index of the medium and the radii of curvature of the two surface of the lens. And from the name, you can say that it is used to make a lens of required focal length from a given glass of given refractive index. So if you have a refractive index, if you have the material which has got the type of a material or the refractive index, you can make a certain type of a lens, which this formula gives us. So now let us start with the derivation. Before starting, we have to consider few things are assumed. Okay, we will adopt coordinate geometry signs, just like the right side will be plus, left side minus, above the principal axis plus and below the principal axis minus. Those are the coordinate geometry sign. And the assumption are, first one is the lens is very thin. Okay, I have drawn this diagram because we need some space in between, but in reality the lens is so thin that the distance measured from the poles of the two surfaces can be taken as equal to the distance from the optical center. Now, let me first of all draw a principal axis. A line passing through the optical center is known as the principal axis. In the center lies the optical center. This side is pole 1, this side is P2, that is pole 2. So it is so thin that P1 and P2 lie somewhere near to the optical center. They don't collide, but they lie somewhere near. Okay, that is the first assumption. Another one is the aperture of the lens is small. This aperture, this area of the lens is taken as small. We are trying to make a lens which has got a small aperture. Third one is the object is a point object. So the object which we are going to consider right now will be a point object, a very small object which lies in the principal axis, which like a small dot. Okay, the object will be a very small dot. Fourth one is the incident and the refractive rays make angles with principal axis. So if object lies in the principal axis itself, the incident ray will make angle with the principal axis. Another thing is we are considering a convex lens made up of glass of refractive index N2. This lens has refractive index N2 placed in a rarer medium of absolute refractive index N1. So this medium has got refractive index N1. Let P1 and P2 be the poles, C1 and C2 be the center of curvature. So if you consider this surface, the center of curvature for this particular surface lies this side, somewhere here. So this is C1. Center of curvature for left surface, center of curvature for right surface will lie somewhere here, that is C2. and R1 and R2 be the radii of the curvature. Radii of the curvature means distance from this point to this point is radius. Okay, radius of the curvature represented as R1. This is distance from center of curvature till this point, that is the pole. Okay, similarly from this point till this point, C2 will be radius R2. As it has two curved surface, it will have two center of curvature, which is and two radius, which is R1 and R2. Okay, now we will consider the thickness of this one to be T. T is the thickness of the lens. So with this, let us start this derivation. Okay, these are the few considerations. Now the first thing is, let a point object O be placed on the principal axis. Okay, we will consider a point object O which is kept on the principal axis. The distance, if this is the object distance will be U. Object distance will be U, which is measured from this pole to this one. Not from pole, but from center of curvature. Okay, from center of curvature. A ray OA, now from this one, incident ray will fall onto the lens. That ray will be OA. So before drawing a ray diagram, what we need to draw is, we need to draw a normal, because without normal we won't be able to measure the angle. So let us first of all draw a normal. Now I have told you, if it is a round surface, curved surface, the normal of that curved surface will be from the center. So normal for this surface will be from the center. Let us draw a normal from the center of curvature. So this dotted line is the normal from the center of curvature for this particular surface. So I will note it as, this is C1, over here is A, this point is A. Okay, so C1 A, and this point is N1. So C1 A N1 is normal for this first curved surface. You please write it down. Okay, whatever I am saying right now, please note it down. So now a ray of, if this is an object, light will fall on this object, and it will from this object, it will fall onto the lens. So let us draw incident ray from object O, and it falls on the lens at this point A. So object will fall from O A. Okay, this is the incident ray, and angle is made between principal axis and the incident ray. Now a ray OA traveling in the rarer medium N1 is incident on the first surface of the lens. It is refracted into the denser medium N2. Okay, there is a denser medium N2 along AB. Okay, AB is a line over here. Okay, I'll just draw a line AB. This is a denser medium, so whenever a light falls on a denser medium, what happens? From rarer to denser, it moves towards the normal. It will not go away, but it will fall towards the normal. So a ray of light B will move towards the normal. It will not make it a straight, but a little tilted line. This point over here is B. Okay, it will bend towards the normal. Now next what happens is, if the second surface of a lens was to be absent. Now, what we are considering over here is we don't have this second surface of the lens. We only have the first surface of the lens. The ray AB would have made the principal axis at I dash. So if we don't have this surface, instead of bending in the rarer medium, what happens? The ray of light will directly fall on this surface, that is this point is I dash. This is when are we considering this point? Suppose this surface doesn't have the second refractive surface, okay? This lens doesn't have a second refractive surface, then the ray will fall on I dash. It will fall on I dash. Now this I dash is actually the image of O due to the refraction at first surface and considering there is no second surface. So now let the distance of I from P1 be V dash. So the distance till here, it is the object distance from V, from this point, it is the image distance V dash. Okay, now then for the refraction at the first surface, using this relation, okay, refraction at the first surface, just write it down. Refraction at first surface. N2 is the refractive index of the second medium. So what is second medium over here? Similarly, N2. V is the image distance. What is image distance over here? It is V dash. So it will be V dash minus refractive index of first medium, N1, divided by object distance, U, is equals to N2 minus N1, which is comparing, okay, R. So what is R over here? We are considering the first curved surface. So radius of curvature for first curved surface is R1. Let this be equation number 1. Okay. Now next, the ray AB traveling in the medium N2 is actually incident on the second surface. But in reality, what we have is this ray AB, okay, which is bending towards the normal, is actually refracted at the second surface. So what happens when okay, I'll compare it with a glass slab. Okay, just compare it with a glass slab. A ray of light falls, it bends towards the normal. Again, from a denser medium, when it comes out of a denser medium, it will move away from the normal. Similar thing will happen over here. First, it enters the lens. Inside the lens, it will move towards the normal, but whenever it is coming out of the lens, it will move away from the normal. Okay, when it moves away from the normal, then the image will be formed. For this lens, this ray of light will meet somewhere here. The ray AB traveling in medium N2 is actually incident on the second surface of the lens and is refracted into the rarer medium N1, bending away from the normal, just in this case, from the normal C2B N2. So we have to draw a normal C2B N2. So from this point also we have to draw a normal touching point B. Okay, so from this point there is a normal touching point B. Okay, C2B N2 is a normal for this point B. Now the ray of light AB, suppose this is bending towards the normal inside the lens. Whenever it is coming out of the lens, it will move away from the normal. The emergent ray, okay, the light which is coming out of the denser medium is known as the emergent ray. So the light coming from this point B is the emergent ray, meets at the principal axis at the point I. So this meets at the principal axis at the point I, which is final real image of O formed by the lens. This is actually the real image of the lens. So this distance of I from point P2 is V. Now for the refraction at second surface. So now refraction at second surface. Okay, for refraction at second surface, I dash acts like a virtual image. Okay, this I dash, it is a virtual object. This is a virtual object. So now the light forms from the virtual object to the lens, and the image is I. So I is the image, real image of I dash. I is the real image of I dash formed by the second surface. So V is the image distance between P2 and I. The distance of I from the pole P2 of the surface is actually distance of I dash. Distance of I dash from P2. If this distance is T, this gap is T. If this gap is V dash, then this distance from P2 to I dash will be V dash minus T. So this distance I dash and P2 will be V dash minus T. If this is T and if this distance is V dash, this particular distance will be V dash minus T. Now for refraction at the second surface from denser medium to the rarer medium N1, comparing with this equation, what we can write is N2 is the refractive index of second medium. So over here, if light is falling from N2 to N1, what is the second medium? It is N1. N1 by V is the image distance. So what is the image distance over here? Image distance is between P2 and I, that is V, minus refractive index of the first medium, that is N2. N2 divided by object distance. U is the object distance. Now what is the object distance? Distance from P2 to I dash, that is V dash minus T, is equals to, it is N2 minus N1, refractive index of medium 2 minus refractive index of medium 1. So in this case it will just be the reverse. Our refractive index of medium 1 is N2, so it will be N1 minus N2 divided by radius R. We are considering the second surface, so radius for second curvature is R2. Now over here what we can see is this V dash, okay, V dash is very large, then T is very small because the lens is very thin, so this is greater than T. So over here what we can consider is N1 divided by V minus N2 divided by V dash is equals to N1 minus N2 divided by R2. This will be your equation number 2. Now the next step is adding equation 1 and 2. So we are going to add equation number 1 and equation number 2. In the next page we are going to add equation number 1 and equation number 2. Equation number 1 is N2 minus V dash minus N1 minus U is equals to N2 minus N1 divided by R1. Okay, we are adding, this is equation number 1, okay, with which we are adding equation number 2. So we are adding equation number 2. Okay, instead of writing this one, I'll just add first of all this side, okay, left hand side. So I'll just add the first side, this side plus. If from equation number 2, what I'm writing is the first part, that is n1 by v minus n2 by v dash is equals to, now the right hand side of equation number 1, n2 minus n1 divided by r1 plus the, I'm writing the right hand side of equation number 2, that is n1 minus n2 divided by r2. In the first equation, what we can see is n2 by v dash minus n2 by v dash. This and this gets cancelled. So rearranging this, what we can write is n1 by v minus n1 by u is equals to, from this two equation, what can be taken common is n2 minus n1 can be taken common. Now inside the bracket, this 1 by r1. If you are taking common n2 minus n1, then what you are left out with over here is minus 1 by r2. Okay. Now dividing both side by n1. Dividing both side by n1. So when we divide both side by n1, I'll just write it down over here. n1, and this is also divided separately. We are going to divide n1, this also n1. Now n1, this also gets cancelled. This n1 gets cancelled. So now what are we left out with? 1 by v minus 1 by u is equals to n2 by n1 minus 1 by r1 minus 1 by r2. This is what we get at the end. Now now what we know is n2 by n1, refractive index of second medium divided by refractive index of first medium is equals to, this is the refractive index of the material of the lens. Just inside the bracket write down the refractive index of the material of the lens with respect to the surrounding medium. So in place of this, we're writing this 1 by v minus 1 by u is equals to n minus 1 inside the bracket 1 by r1 minus 1 by r2. Now what we know is, when the object is at infinity, image will be formed at focus. I hope you know this. This is the property. This is one of the image formation of the convex lens. Okay, when the object is at infinity, image will be at focus. We're replacing this over here. 1 by v, 1 by focus minus 1 by infinity is equals to n minus 1, 1 by r1 minus 1 by r2. Now simplifying this, 1 by infinity is equals to 0. So this part I'm going to write 0. So 1 by f is equals to 1 minus 1, 1 by r1 minus 1 by r2. Now this is the final equation, which is the relation between focal length, refractive index of the medium, okay, or the ratio of the refractive index of two medium, radii of two curvatures. So this formula is known as lens maker formula. With the idea of refractive index, we can actually find out can make a lens of a given with the given information. Now it has been derived for convex lens forming a real image. Okay, this is derived for convex lens which is forming a real image, but it is equally applicable to a convex lens forming a virtual image and to a concave lens which forms only virtual image. Just to remember that. Now this equation is equation number 4. Another equation over here, this equation over here is equation number 3. Now from equation number 3 and 4, what we can write is, right hand side is equal, so left hand side will also be equal. So if left hand side is equal, what we can write is 1 by v minus 1 by u is equals to 1 by f. I hope this is the formula which you have seen multiple times since you have studied lens. This is known as lens equation, or full name is Gaussian form of lens equation. Now, in examination, there might be two types of question from this derivation. One is to derive lens maker formula. If that is the question, your derivation is up to this equation. Okay. Now, it might also be to derive the lens equation. Might be written as lens equation or Gaussian form of lens equation. You have to derive up to this equation. So, this is one of the most important derivation in this chapter, that is lens. Okay, this much for today. We will continue in the next class with another topic from the same chapter. Thank you.